All right, welcome back, everybody. I guess this is lecture 2b, or the fourth time we've met today, or this semester. Today, we're going to continue our discussion on open systems, how we deal with conservation. Oh, thank you. I appreciate you continuing to remind me to do this. So we're going to continue today our discussion on open systems. Hopefully get to do an example with conservation of mass and with conservation of energy, and then still have at least an hour left to do to talk a little bit about review. So if you have questions. Now, I'd also like to remind you that we do have office hours tomorrow. I believe the times are 3 to 4 tomorrow at the same Zoom link as the class. So if you do have other questions in preparation for the examination, you're welcome to ask them in office hours as well. So we have a 6:30 start on Monday, unless you've arranged a separate time with me. I think I responded to everybody who has asked for separate times, but if not, please let me know no later than tomorrow. Again, a reminder that the exam is going to be on Monday at 6:30. So nominally, the exam will begin at 6:30, and it'll have 3 different components, but you won't be able to access the whole exam at once. We'll sort of segment it into 3 different pieces with different due dates and a little bit of a break in between the parts. Right. So again, if you do have conflicts or you're looking for a separate time, please let me know as soon as possible, no later than tomorrow. So we've been talking about conservation of mass. Conservation of mass is extremely important in thermodynamics because we know that mass carries energy with it, right? That's one of the things we've learned when we were talking about closed systems, because that's sort of everything we were learning on the left-hand side of this equation here. The delta E, after we made some assumptions, became the change in internal energy, or mass times the change in specific internal energy. In order to figure out that little u term, we needed to figure out what the fluid was. Was it water or something like it, like a refrigerant, something that's going to move back and forth across the vapor dome where we have phase changes that are important? Or is it going to be something like an ideal gas? And we have different strategies for finding the different properties in both of those cases. But last class, we started to get to the point where, what if the answer to what's going on with the mass is that mass can enter and leave the system, right? So conservation of mass is important. There are lots and lots of mechanical engineering components that we're interested in that have open systems, right? So that have mass coming in and out, right? So this internal combustion engine is one of the pictures from the textbook, and we can see that there's air going in and there's fuel going in and there's exhaust gas coming out. So this is an open system. So we started to ask the question, what happens to the mass last class, right? And at first we started talking about this elapsed time equation, but we essentially never deal with the elapsed time version of this equation. But we did use this to sort of introduce this idea of steady state, that you can get to this thermodynamic equilibrium where none of the properties of the system are changing with time, including the mass that's stored inside the system. The more common version of this equation that we'll use in this class is the rate version of this equation, where we essentially, instead of looking at a process that's moving through time, we take a snapshot and look at the rate of change of something like mass in the system, right? So there we saw that the rate of change of mass in the system is equal to the sum of all the mass flow rates in minus the sum of all the mass flow rates out. Okay, thanks for the note, just someone's leaving and coming back in. So again, we have this important case of steady state, right? And that would be the case in an open system when we're talking about a snapshot, is I'm leaving my T-mug out in the rain, right? But it's also got a hole in it. So there's mass coming in. There's some mass flow rate coming in. There's some mass flow rate going out, but if those two things are equal, then the amount of mass in my cup, or the level of the height of the water in my cup, stays the same. Because the mass in the system is a property of the system, when we're at steady state, the amount of mass in the system stays constant. So there is no increase or decrease in the mass of the system at steady state. And when we're there, which is what most of this class will focus on, we know that the sum of the mass flow rates in is equal to the sum of the mass flow rates out. If you go on to take Thermodynamics II at RIT, then I think you start to deal with some transient systems where you start to be interested in this differential term, and you might have to do some calculus to figure out how the mass is changing with time. But for us in this class, we will always be at steady state. So we're going to do this problem. So this is a turbine. If you're not familiar with what a turbine is, it's essentially, it's like a windmill, right? So one of the reasons that we like this idea of boiling water is when we boil water, it turns into steam. Right? And steam takes up a lot more volume than liquid water. So that steam expands, right? And it wants to go somewhere. So we funnel it into something like a turbine. And inside this turbine are some fan blades. And as that steam runs across those fan blades, it generates a force which turns that shaft. So we're turning heat energy, which often, if you think about a coal power plant, is energy that was stored chemically in fossil fuels. We burn that to get heat, and then we're turning that heat into steam, and then we use that steam to generate this mechanical power. In this particular turbine, there's one inlet and two outlets. We're given some information, but we're asked to find the velocity at my two outlets, outlet 2 and outlet 3. So let's take a look at how we would go about solving this problem. Right? So this is the same problem. We're told some state information, and just in general, this is a good habit to get into, that when we're given states, to make a state table. Right? So here I have my state numbers and then the different properties that are associated with the mass at these different states. Now, when we were talking about closed systems, our state numbers referred to instants in time. But in open systems, these state numbers are about points in space. Right? So when we talked about open systems, the first thing we said was we had to draw a control volume. What's the part of the universe that I'm interested in? And here, it's this turbine. And we see in the turbine, most of these walls are solid, but there are some points at state 1 and state 2 and state 3 where mass can cross my boundary. And that's what makes this an open system. So we're asked to find the velocity at state 2 and the velocity at state 3. Right? We have this nice picture. We're told some information. Now, usually if we're asked to find a velocity or a mass flow rate, we know we're going to use our conservation of mass equation. It's also kind of a giveaway in this particular lecture because this lecture is about conservation of mass, right? So it's not surprising we're going to use conservation of mass here, right? And we also remember, maybe, that we said that the mass flow rate is area times velocity divided by specific volume. Now, for your exams, they'll be open book because it's an online class. But if you go into the materials for the course, there's an equation sheet that I've developed, which is the one that I like to use when we're teaching the class. And it's kind of one sheet, and it's got all the equations that I think you need. Now, you can go through and make a similar sheet. You can even put more information on it if you like. But I think that equation sheet is all you need. And both of these equations are on there. Just a reminder, one of the ways we can see that this mass flow rate equation is reasonable, right, is we have area which is in meters squared. We can check the units, right? Multiplied by velocity, which is meters per second, divided by specific volume, which is meters cubed per kilogram. Right? This is also a trick if you look at an equation and you're not sure when you see a V here, does that mean voltage? Does it mean velocity? Does it mean volume? I'm not sure. Right? So you can always go through and check the units and see if it would make sense. Right? So here, if I multiply meters squared by meters, I get meters cubed in the numerator of the numerator, but I also have meters cubed in the numerator of the denominator. So this is 1 over seconds divided by 1 over kilograms. But if I have something in the denominator of the denominator, I can put it up into the numerator. So this becomes kilograms per second. So hopefully that increases your confidence that this particular equation is reasonable to try to find the mass flow rate. Now, one of the assumptions that we don't often write down is that to use an equation like this, we're assuming that the properties at the inlet are all constant, right? That even though there may be some velocity distribution at this inlet, we're going to say, well, I can just say whatever the average velocity is, that's reasonable there, right? Or, maybe there's some temperature distribution at this inlet too, which means there'd be some distribution of density or a specific volume. But we're just going to assume that all the properties at each of the inlets and each of the outlets are constant. Right? Now, when I usually think about tracking my assumptions, they're the assumptions that I need to make to do the solution. Right? So here, I'm going to start with conservation of mass. And you'll see, if you do this on your exams, this is why I always encourage you to start with the base level equation. So the equation that you'll find on the equation sheet that I wrote down. Because if you do that, then in order to get to a symbolic solution, you have to tell me what your assumptions are. Right? So in this case, we'll say that this is at steady state. So that, the turbine's not kind of warming up. We didn't just turn it on. It's been running for enough time that all of these properties are not changing with time. In this case, we know that there's only one inlet, but there are two outlets, right? So that means that the mass flow rate at the inlet, which is state 1, has to be equal to, well, let's do it this way. Because it's the sum of the mass flow rates in. There's only one inlet mass flow rate minus the sum of the mass flow rates out. That's m dot 2 minus m dot 3. Right? And that's all equal to 0 over here. Or I could rewrite this equation to say that m dot 1 is equal to m dot 2 plus m dot 3. And this is nice. This is a great equation. Unfortunately, it doesn't help me answer the problem. Because what the problem asked me for, so I'm looking for the velocity at state 2 and the velocity at state 3, and I can't use this equation yet to find either of those two things because velocity is not in either of these equations, so I can't solve for it. Right? So now I need to use the equation. So here, if we call this equation 1, then my equation 2 will be that mass flow rates are equal to areas times velocities divided by specific volumes. And I can put that into this equation, and that's going to tell me that the area at state 1 times the velocity at state 1 divided by the specific volume at state 1 is equal to those same things at state 2 and state 3. Does that part make sense? Okay, so let's see what we know. All right? So here we know pressure and temperature at 1. Oh, we know AV1. So I don't know the area or the velocity over here, but I know them both as a group. Now, sometimes it will tell me A1, V1, right, separately, but it might tell me that this is a volumetric flow rate. Because A1, V1, right, if we look at the units there, just a sec, Jules, this is going to be meters squared times meters per second, and that's going to give us meters cubed per second. So if you were, let's say you wanted to measure the flow rate coming out of a garden hose, you might get like a 5-gallon bucket, turn on your hose, and time how long it takes for you to fill up that 5-gallon bucket. But that 1 gallon is like it's a volume. So really you're measuring the volumetric flow rate. And then you'd need the density or the specific volume to figure out the volumetric flow rate. Now, I did see a hand up there. Did you still have a question? Oh, for some reason, there we go. I can hear you now. I didn't hear you there. I don't know if my speakers aren't on. Can you try again?
Can you hear me now?
Yes, I can hear you now.
Okay. I was just wondering why they're all V1 instead of different velocities in that.
Oh, so this one should be AV1, and this is A2.
At velocity. Yeah, at the bottom.
Oh, that's because I made a mistake. Thank you. So you're right. This should all be relating to state 2, and this should all be relating to state 3, and this should all be relating to state 1. So thank you very much. Maybe it's not quite as applicable here on Zoom, but I had a speaker come in and she sort of said, you know, sometimes when we feel like we're teaching, you know, the like 2 feet away from the board is kind of like the zone of stupid. So it's really easy for us to make mistakes when we're trying to do these things. So please point out anytime you think I make a mistake, because it's not uncommon that it happens. So I appreciate that.
Thank you.
You're welcome. So here we know this area times velocity. We know that at 1. I don't know any of these specific volumes, I don't think. Right? But I am told my diameters, right? And I know that I can either say that area is equal to pi d squared over 4, or pi d over 2, which is the radius, squared. Oh, just pi r squared, right? Right, so that's the same thing. So even though I don't have that, so actually in my equation here, right, I have to sort of work on this a little bit to say pi d squared over 4. This is d2 squared over 4. v2. Oops. That's not v2 squared. Divided by the specific volume at 2 plus pi d3 squared over 4 v3 over my specific volumes. Right? And now we know these diameters, but I don't know the velocities. Those are the things that I'm trying to find. And hopefully these, if I can fix the states, then hopefully I can find those. So this is not bad, right? I mean, maybe it looks bad because I got 1 equation and 5 unknowns. So normally you'd say like, that's bad, right? But in thermo, 3 of those unknowns, if we could fix the states, then I could get those numbers. But I still have a problem here because I've got 2 velocities here that I don't know. So I'm going to look back up at the problem and see if there's some other piece of information that'll give me some other equation. Because even if I could fix all of these specific volumes, I'd still have 1 equation and 2 unknowns, which means that I can't get an answer, right? So in this case, there is something else that they tell me, right? And here, what they tell me is that 20% of the inlet mass flow rate comes out at state 3. So I could, there's a couple different ways I could solve this, right? So it's good. So I have a separate equation. So that's my equation 1. If I go down here to equation 3, this tells me that 0.2 times m dot 1 is equal to m dot 2, which I could write, if I wanted to, as A1 V1 over specific volume at 1 is equal to 1 over 0.2 times A2 V2 over specific volume at 2. I like this equation a little bit better because here I know that volumetric flow rate. I know, well, I hope that I can fix these two things. I know this area at 2, right? Because it's going to be this pi d squared over 4. And then this thing that I'm trying to figure out, this velocity at state 2, I could get over here. So from this equation, I could get one answer that I'm looking for as velocity at 2 is equal to, it's funny because I got to undo this division, right? 0.2 times A1 V1 over the specific volume of 1. Right? But I got to multiply, I did that already, right? I also got to multiply this by the specific volume at 2, and I have to divide by the area at 2. I can just quickly look at units here, right? So if I look at units, this specific volume is meters cubed per kilogram. My fraction has no volumes, no units, 0.2. This area is going to be meters squared times velocity is meters per second. And then in my denominator, I'm going to have meters squared down here. And this specific volume is going to be meters cubed per kilogram. And this is a nice thing because this area, unit-wise, is going to cancel with that area. This specific volume is going to cancel with that specific volume. And I'm going to get an answer in meters per second, which is nice because I want a velocity, and that's distance over time. So I like this equation, right? This is going to be, I guess we're at equation 4 now. The good news is for this equation that I know A1 V1. I can find A2. I just have to fix my states. I really have two options for finding the velocity at 3. The first is that I could take this equation and put it into this equation over here, which is, well, I guess I skipped a number. But I could put this up into this equation here and then solve for V3. But I think that's going to be pretty cumbersome. Instead, what I'm going to do is I'm going to put this equation back into equation 1. Right? And if I do that, what I'm going to find is that this is equation 1 up here, right? But that's going to tell me that m dot 1 is equal to m dot 2, which is 0.2 m dot 1 plus m dot 3. And this is because it's at steady state. So because it's at steady state, if 20% of the mass flow is coming out at state 2, and we're at steady state, that means I'm not accumulating or losing any mass in my system. Well, that means in order to make this whole, in order to conserve mass, m dot 3 has to be 0.8 times m dot 1. And then I can take this and do a pretty similar manipulation that I did over here, and I get the velocity at 3 is going to be equal to the specific volume at 3 times 0.8 over the area at 3 times A1 V1 divided by the specific volume at 1. And this will be my equation 5. So if I look at this equation, I start to do some accounting, right? I need to fix the state to get V3. A3, right? This is pi d3 squared over 4. A1 V1 is given. I need to fix the state to find the specific volume at 1. Right? So if I could fix, this is going to be pi d2 squared over 4. So if I could fix states 1, 2, and 3, then I'd be able to put numbers into these equations and get answers. That make sense? So now this is when a state table comes in handy. So I'm going to see if I can capture this and copy it down. To the next page here. So here my pressure is going to be in kilopascals, right? So I know that I have two states where I have temperature and pressure. I'm not 100% sure I can solve these two states, right? Because I can only solve states with temperature and pressure if they're subcooled liquids or they're superheated vapors. But this state 3, I know automatically this one is two-phase. Right? So let's check these out first. So I have 1,000 kilopascals, which is 10 bar, which is 1 megapascal, right? And the other one is 0.8 megapascal or 8 bar. So I need to go down here to my state tables. So I have 10 megapascals, right? And in this case, the saturation temperature, it tells me, is 179.91. But I think we're at like 500 degrees, right? Something big anyway. Yep, 500 degrees for state 1, 400 degrees for state 2. So for state 1, I'm going to look for 500 degrees. It's lucky that it's right on the line here. My specific volume is 0.354. If we're talking about state 2, it was at 8 bar or 0.8 megapascals, and it was at 400 degrees. Here it tells me that water boils at 8 bar at 170 degrees, or a little bit more than that, but 400 is much bigger than that still. So here, this is 0.384. So then the other state, so I have 0.354 and 0.8384. Now for state 3, I know that the quality is 0.9, which is a dead giveaway that it's two-phase. I'm also told that the temperature is 90 degrees. So if this was a textbook problem, I would look on table A2. That's where I would look in the textbook tables. Here we have a table that's a little bit different than that. It's the table from the FE handbook. But this is like table A2 because the temperatures are nice round numbers here on the left. I know that I have 90 degrees So VF is, again, about 1 over 1,000, and VG is 2.36. So here I know for state 3, VF at 90 degrees is about 1 over 1,000 meters cubed per kilogram. VG, was it 0.36? Now I gotta go back and look. I should have put it in the chat, then I would remember. 0.236 or 2.36. 2.36 meters cubed per kilogram. So now this is the weighted average, right? So V3, which is a function of x3, is going to be equal to VF plus x3 times VG minus VF. If I was in a rush on an exam and I didn't think I would be able to finish, I would write this equation out, but then I would just take this number times 0.9, because this 1 over 1,000 is going to be so small that it's not really going to affect my answer. But if I take 2.36 minus 1 divided by 1,000 times 0.9 plus 1 divided by 1,000, and I get 2.124 meters cubed per kilogram. Does it make sense how we fixed these three states? Both of the first two states were superheated vapors because the temperature, so for states 1 and 2, the temperature was bigger than the saturation temperature, which is the boiling temperature, at the given pressures, P2 or P3, right? Because this was like, whatever, it was 179 and 170 or something like that, right? But we're up at 500 and 400. So those were superheated vapors. So now, if I took those numbers, instead of doing the arithmetic in front of you, this is all just the same stuff, right? Then I could put those into the equations that I had for velocities. Here, I guess first, numerically, I found numbers for the mass flow rates, because they told me the volumetric flow rate, or the area times the specific volume at state 1. And then I divided by the specific volume at state 1. And that gave me some mass flow rate. I do have to be tricky. I do have to be careful about the units. I like mass flow rates where the unit of time is seconds. It doesn't really matter. But you know, because if you just had kilograms per minute, it's just a different number, right? But just be careful and look on exam problems, because I'll tell you sometimes what unit that I want. If I don't tell you what unit that I want, then there's no difference between kilograms per minute or kilograms per second, right? So I know there's 60 seconds in a minute, so I took this number divided by 60. I got 11.1 kilograms per second. 20% of that comes out at state 2. So that's 2.2 kilograms per second. 80% of that comes out at state 3. So that's 8.9 kilograms per second. Right? And this is exactly conservation of mass. That because we're at steady state, then the mass flow rate going in, the sum of the mass flow rates going in, is equal to the sum of the mass flow rates going out. Here, I remember they told me these diameters. So I calculated the areas is pi d squared over 4. It was nice they told me the areas in meters, so I didn't have to mess around with the units here too much. So then I can find my two velocities, and I found out that the velocity at state 2 was 17.1 meters per second, and the velocity at state 3 was 10.7 meters per second. So do we get the idea of the process here for a conservation of mass type problem? Okay, that's good. Now, anytime we answer a question, right, we kind of want to ask ourselves, does it make sense? Right? And here, it's a little tough because I know the magnitudes and I know the signs and I know the units. But I don't really have a sense of the magnitudes necessarily, right? But I do get units that are in distance per unit time, which makes sense for a velocity. These values are positive, which means that when I assigned them as inlets and outlets, I was correct. If I get a negative velocity, what that means is that I thought the velocity was coming out, but really the velocity is going in, which might be a hint that I made a mistake somewhere. So it's nice that both of these are positive. But I don't know. Does it make sense that the velocity at state 2 is bigger than the velocity at state 3, even though there's, right, this was only 20% of the inlet mass flow, and this was 80% of the inlet mass flow, right? So how come this velocity is higher, right? And we have to remember, conservation of mass is about conserving mass. It's not about conserving velocity. It's also not about conserving volume. So the volumetric flow rates might be totally different. If you imagine a pipe where liquid water is going in and steam is going out and the diameters stay the same, the velocities will be very different. The volumetric flow rates will be very different, even if you're at steady state. But if you're at steady state, it's the mass flow rates that get conserved, right? The volumetric flow rates are only conserved if this specific volume doesn't change. All right, so the take-home message is that it's mass that gets conserved and not velocity and not volume, right? So we can, it's just like so many of these things. I don't really have a good enough sense to tell you, oh, the magnitude of that number makes sense, right? But I know the units are right. The sign makes sense, right? And I could argue either way that one is supposed to be bigger than the other. Right? So that's how we do conservation of mass problems. Does anybody have any questions? All right, we'll take a break for 5 minutes and we'll come back at 7:13. All right, everybody, thanks for coming back. This next part, we're going to introduce the equation for the first law in open systems. I'll walk you through a little bit how we get to that equation, but you're never going to have to derive this on an exam, just like conservation of mass or the closed version of the first law. We're just going to have to use this equation, but I still want to show you where it sort of comes from. Right, so we've been talking about these open systems where mass can come in and out of our system, right? Can cross the boundary of our control volume. Anytime we have an open system, the first question we want to ask is, what is our control volume? Where do we draw it? Then we just talked about what happens to the mass. We need to account for the mass. And the reason we do that is because when we start to account for the energy, the mass takes energy with it into and out of the system. So now that we know what happens to the mass, we can start to ask what happens to the energy. So this was our closed system energy balance, or our closed system first law, right? The change in the energy in the system is equal to the heat transfer in minus the work going out. When we talk about open systems, we stop talking about elapsed time equations and we start talking about rate equations. So all I did between these two slides was I divided all three terms here. If you think about the delta E term on the left as one term, divided them all by delta T, the change in time, and just made that time really, really small. And then we get the calculus version of that equation. Again, for things inside of our control volume, like the energy stored in the system, they get the differential term. But things that are crossing the boundary of our control volume, like the heat transfer and the work, they get a dot to show that even at steady state, those things don't have to be zero. Right? Now, if I look at this, right, and I start to think about open systems, can I still transfer heat? Yeah, of course I can, right? You could think about a duct that was carrying air, but maybe you wrap some kind of electrical heater around it, you turn on your current, and now you're heating that air, right? So yes, you can still transfer heat. That heat transfer term is still going to be important, and it's still going to follow the same sign convention that we had in closed systems, where heat in is positive, therefore heat out is negative. This starts to get a little trickier, right? Can we still get work out of the system? The answer is yes. We talked about that turbine in that open system mass conservation example, but there you have this steam that's trying to expand. It's moving over these fan blades, and that steam is pushing that fan blade and causing a shaft to spin, right? So we're getting mechanical energy work by forcing that pressurized steam over those fan blades, right? So we can still get work, but there's two different kinds of work we want to think about here, right? Now, when we think about open systems, are there any differences, right? And the difference when we're thinking about open systems versus closed systems is that in open systems, energy can come in and out with the mass. So I need to have some kind of energy terms that are associated with the mass flow rate coming in and the mass flow rate going out. So all I do is I take my equation and I add that I'm going to add up all the energy that comes in with the mass, and I'm going to subtract all the energy that goes out with the mass. And again, because this is the rate equation, we talk about the rate at which energy is entering my control volume by mass. That's this first term. And the rate at which energy is exiting my control volume by mass. Right? So this open version of the first law is telling us that the rate of change in energy in the system, we can figure that out by looking at the rate that energy is coming in by heat transfer minus the rate at which energy is leaving by work, plus the net rate of energy coming into the control volume by mass, right? So that's the energy that goes in with the mass minus the energy that goes out with the mass. Right? Now, don't worry about writing this derivation down. Again, all these notes are posted, right? And we're going to just get to the final equation, and the final equation is the one you're going to see on the equation sheet. That's the one we're going to want to work with. But I want to show you how we get there, right? Now, the work term's a little tricky, right? So just like there's, the problem that we did last time with the paddle wheel inside the piston, and there was two different kinds of work, right? There was the pressure work, right? The gas pushing on the piston, but there was also that work happening inside the control volume because that paddle wheel was turning. And this is also true inside a control volume. So if I have steam that's flowing through a pipe, what happens is the pressure decreases as I move along this pipe. And that's because the universe always has to get paid, right? So if I took a bowling ball and I rolled it down the hallway here on campus, the ball slows down, right? Because there's friction on the, where it meets the surface, right? And that friction robs it of some velocity. But here in a pipe, provided that the areas are the same, right, and the densities or specific volumes stay the same, I'm not allowed to have friction reduce the velocity of my fluid, right? Because if I did, I would violate conservation of mass. So what happens here is that the pressure decreases, right? So pressure is another form of energy, right? So friction in the pipe, and there's still friction in the pipe, right? It's going to take away from the pressure in the flow instead of the velocity of the flow, right? So there's the rate of work due to pressure, because if these pressures are different, Now there's a force imbalance across my control volume, right? So there's higher pressure inside my hose than at the exit, and that's what's pushing that liquid out of the hose. But then there's that other thing, that paddle wheel work, or the work that's happening inside my control volume. In that turbine, this is the fan blades, right? And if that steam runs over those fan blades, it causes that shaft to turn. So there's that other kind of work, the work that's happening inside the control volume. This term always sticks around in components that have fan blades inside of them, right? So for us, that's going to be, we're going to talk about turbines a lot, but it's also true with pumps. If you look at a pump, it has a fan blade. Sometimes we might call that an impeller, right? You plug that into the wall, you turn the pump on, and it spins that fan blade around. That increases the pressure of the water in your pump, which forces it to come out, right? So there's this kind of fan blade work, or the work that's happening inside the control volume. So this pressure work, right, is going to be, we're going to find that out by looking at all the inlets and outlets, taking the pressure times the area multiplied by the velocity. This isn't really work, right, because it's work with a dot on top of it, so it's work per unit time or power. So there's some power that's being developed because of the change in pressure in my flow. Right now, just to show you, or hopefully build your confidence in this equation, we have power, which should be in joules per second. Pressure is in newtons per meter squared. Area is in meters squared. So newtons per meter squared times meter squared gives us newtons. Then times meters per second gives us Newton meters per second, which is joules per second, which is also power. But we can also think about this, right, as the mass flow rate times the pressure times the specific volume, right? So I know that the specific volume, so I have a definition for mass flow rate, which is area times velocity divided by specific volume, right? So I can take the area and the velocity out here, and I can multiply by specific volume, right? But again, to kind of show you that this still works when we're talking about power, for this equation, I have the mass flow rate in kilograms per second times the pressure in newtons per meter squared times a specific volume, which is in meters cubed per kilogram, right? So here, the kilograms are going to cancel out. Meters cubed divided by meters squared is meters. So I get Newton meters per second, which is joules per second, right? So this equation still looks good, right? It still kind of works. And I can put that in for my pressure work, right? So this was, I had my work because of the fan blades, and then the pressure work, or the pressure power term, still sticks around in there. Now I can start to break down, or maybe expand, this energy, the rate of energy that's coming in or going out with the mass. Just like in our closed first law, we know that this energy can take different forms. So it can be internal energy, which we've spent a lot of time talking about now. It can be kinetic energy. This is per unit mass. So that's just V squared over 2. Or it can be gravitational potential energy, which is G times Z. Right? So internal energy, kinetic energy, and gravitational potential energy. Right? So all those, the mass can be carrying all those types of energy with it. Right? So now if I want to check the units, mass times specific internal energy, mass flow rate is kilograms per second times kilojoules per kilogram. The kilograms cancel and I get kilojoules per second, right? Which is power, right? Energy per unit time. It gets a little trickier with these other two unit types, even in the metric system, right? So now I've got mass flow rate, kilograms per second, times the velocity squared, right? So that's meters squared per second squared. Right, so now I can make this 1 over seconds times kilogram meters per second squared, right? But remember Newton's law? Newton told us that force is equal to mass, kilograms, times acceleration, meters per second squared. Now times meters. So this is just newtons in this square bracket here. So this is 1 over seconds times newtons times meters, or joules per second. So this is still energy per unit time, right? But typically, if this kinetic energy term sticks around, we're going to divide by 1,000 if it's metric, because probably our velocity will be in meters per second and not kilometers per second. So, and I guess even that would be messed up, right? So we got to carry our units basically anytime kinetic or potential energies stick around. We get a similar thing when we look at the potential energy term. That's kilograms per second, again the mass flow rate, times g, right? That's an acceleration due to gravity, so meters per second squared, times meters. So again, I've got mass times acceleration. Newton told me that's a force. So there's 1 over seconds times newtons times meters, or joules per second. Again, energy per unit time, or power. Right? Again, if this term sticks around, we got to worry about the units. So this is what our equation looks like, but we can make a simplification. Right? So here we have some terms that are multiplied by the sum of the mass flow rates in, circled in red here. Some terms that are multiplied by the sum of the mass flow rates out, or at the exit, circled in green here. So I can group those terms together, and my equation gets a little bit less messy here. Right? So now I still have dE by dt, or the rate at which the system is storing or depleting energy, is equal to the rate that heat transfer comes in minus the work that goes out by fan blades in the system, plus the sum of the mass flow rates times all this stuff in the brackets. Now, inside the brackets here, there's this specific internal energy plus pressure times specific volume. Now, let's say it was steam and I was given a temperature and a pressure. I would go to my tables and I would find the specific internal energy. And then I would have to go to my tables and find the specific volume. But as long as I was given the temperature and pressure in those cases, right, U would always be the same in that state, and V would always be the same in that state. So why would I look up both of them at the same time? Right? That's like doubling the work. So instead, or the effort, let's say, so we don't confuse it with thermodynamics, right? Now, what we can do is we can define a new type of property. And that property is going to be specific enthalpy. Little h is equal to U plus PV. Now, we talked about how specific enthalpy is on the tables that we look at, but we never really talked about why. And the reason why is so that we can be more efficient when we're trying to fix the states here, so that I don't have to find specific internal energy and specific volume at the same state, when once I know one of those things, I'm probably going to know the other one of those things automatically. So why not combine them together, and that makes our lives easier. So if you look at an example or the equation sheet that I have posted on my courses, this is the open version of the first law of thermodynamics. And this is really what I think we should start. Any open first law problem, we should write down this version of the equation. I know it's going to take a little bit of time, but what's going to happen is for each system, we're going to make different assumptions and we're going to cancel out a bunch of these terms. But if you always start by writing out the whole equation, then what happens is you have to tell me all the steps you went through to get to the final equation that you're going to get, right? So if you force yourself to start from this base level of the equation, it's more likely that you'll be able to demonstrate your understanding of the material by the time you get to the end. And it's definitely one of the things that people often miss points on in exams is they don't tell me the assumptions that they're making, right? But if you force yourself to start from this version of the equation, then it's a lot easier to write those things down, right? Now, when we talked about conservation of mass, we talked about steady state, right? That was the thing when interesting things were happening. There's still mass going into my cup. There's still mass coming out of my cup, but the water level stayed the same. This is also going to be true for conservation of energy, right? It's a little harder to picture with my cup, but you could think about something like my phone, right? So if you could maybe imagine a case with my phone. Now, this is different because we're not talking about mass going in or out, right? So, but it's still sort of similar where maybe I'm watching some kind of video and that's a big drain on my phone, right? But it's storing or depleting energy in the battery. So if I plugged it in and it's charging at the same rate that it's discharging from use, then the amount of energy stored in the battery would stay the same, right? So that's kind of the same idea as the cup, right? And if we were at steady state with my cup with mass coming in and mass going out, as long as the properties of the water that stayed in my cup stayed the same, so it stayed at the same temperature and pressure, for example, then the energy stored in the mass in my cup would also stay the same. So if this is at steady state, what we do with steady state is any term that's d something by dt goes to 0. So at steady state, this differential term goes to 0, and we're left with this equation, but there's 0 on the left-hand side, right? And again, in this class, in this Introduction to Thermodynamics class for mechanical engineers, we're always going to be talking about steady state, right? This equation is specific to the metric system, right? Now, if you went through those first 3 lectures that we didn't talk about in class, you notice that it starts to talk about things like weight versus mass, and how that always gets a little bit messed up in the imperial system because you have pounds force and you have pounds mass. In some mechanical engineering classes, we get around this issue by talking about slugs, right? Where slugs is like an imperial unit of mass that's equivalent to kilograms. And then you can use Newton's first law or Newton's second law to say that the slugs times the acceleration in feet per second is equal to a force. But if you're talking about mass in terms of pounds mass, like we usually do, then what happens is not only do you have to worry about unit conversion here, if you get potential or kinetic energy and they stick around, you have to divide by GC, right? This is kind of a funny thing, right? And it's this artifact of there being of 1 pound mass having 1 pound weight, right? Even though you know that force or weight is equal to mass times acceleration, right? But if you have 1 pound of mass times a gravitational acceleration of 32.2 feet per second squared, well, you don't get 1, right? So GC has a magnitude of 32.2. It's also like an acceleration, so it's got feet per second squared. But then it's also got in the units, we got to change that pounds mass to pounds force. So we have to take that. So its units are not just feet per second squared, but then also pounds mass per pound force. That's also on the equation sheet that I provide for the course. But the thing is, it's always the same 2 terms. Even in the metric system, if my velocity was in meters per second, or my elevation was in meters, then I had a problem with units here because I'd have to divide by 1,000 because these terms would give me joules per second and this term would give me kilojoules per second, right? But in imperial it's worse because not only do we have to deal with units, because probably these are going to be in foot pounds and these are going to be in BTU, H is going to be in BTU per something, right? So we'll probably also have to divide by 778 which I guess is kind of like the imperial equivalent of 1,000. So the moral of the story here is if kinetic or potential energy stick around, you need to be aware of the units. You really have to track your units in your calculations. This is, on day one, I said, thermo is a class that a lot of people kind of love to hate. And part of the reason is we got such funny units. When we talk about air conditioners, my air conditioner developed a leak because it had a clog. So all the condensate was leaking all over my basement floor, which is, it's only a 2-year-old air conditioner, so it was kind of a pain. But when we bought that air conditioner, central air systems are not rated in BTU per second or something like that, right? Instead, they're rated in tons, right? And you might think that tons is a unit of mass, and it is, but it's also a unit of heat transfer rate, because it's about how much heat do you have to add to melt 1 ton of ice in a given amount of time, right? So it's, we got all these really weird units in thermodynamics, so we always want to carry our units in our math, right? So it's always going to be this kinetic and potential energy term, if they stick around, that gives us problems, right? So here, again, right, so if we have pounds mass per second and we multiply that by BTU per pound mass, which is what H is when we look it up. This one's nice. It's in BTU per second. BTU is energy second, so this is energy per unit time. This one starts to get a little trickier, right, because we've got mass flow rate, pounds mass per second, times velocity squared, feet squared per second squared, and then 1 over GC. Right, so if you flip this over in your head, GC is kind of like an acceleration, so it's feet per second squared. So 1 over GC would be second squared per feet. But then it's also got this term where if we think about the Newton's second law, then we got to change that pounds mass into pounds force. Right, so if I do this, I get foot pounds per second, right, which is good because it's energy per unit time, but it's not BTU per second. Right, so I want to change those foot pounds into BTU if I'm adding this to an enthalpy value that I look up in the textbook. Right, so I don't just have to remember to divide by GC in imperial units. I also have to look at my unit conversions. I'm probably going to have to divide by 778. It's similar for potential energy problems. Again, I have a mass flow rate times G, which is an acceleration, which is feet per second squared. GC is kind of like an acceleration, so that feet per second squared inverted is here. But then there's also this pounds mass per pound force thing. And again, I get foot pounds per second. And again, I got to turn that into BTU by dividing by 778. Right? So kinetic and potential energy are always a problem if we're not canceling those terms out. But they're more of a problem in the imperial unit system, which I'm sure is not a surprise because... right, it came out after. So, when we made up metric, we sort of learned from all these things, right? I mean, they made up the imperial system before they knew what mass was. So they thought that making 1 pound mass having a weight of 1 pound force made sense. And it does, unless you're an engineer that's doing calculations, and then you're in trouble, right? Because it's kind of a pain, right? But those two terms, if they stick around, your spidey sense has got to start tingling because units are going to be a problem. Right, so we'll take a break here for 5 minutes and we'll start to look at what we do with this equation. So we'll take a break till 7:45 and then we'll come back. I'll show you generally what we do with a whole bunch of different open system types, and then we'll do conservation of energy on that turbine problem that we did conservation of mass for. So I'll see you in 5 minutes. All right, everybody, we're back. We've been talking about, open systems. So we need to understand where to draw the control volume. We need to know what happens to the mass. And once we know what happens to the mass, then we can figure out what happens with the energy. Right, so we just talked about this open version of the first law of thermodynamics. So we need to know something about the heat rate in, the work going out by fan blades inside the control volume, and then that mass comes in and out, or that energy comes in and out with the mass. Anytime I get kinetic and potential energy sticking around, I know that I'm worried about the units, right? So that's going to be an issue, right? Especially in imperial problems, where we need to not only worry about the units, but just to get the right quantity, to get the energy per unit mass, we have to take these terms and divide by GC. Right? So that's only really going to be an issue, though, if kinetic or potential energy stick around, which is often not the case. Right? So hopefully, now again, I'm biased here, right? But hopefully we're starting to learn how understanding the first law really gives us a window into how the universe operates, right? But it's a good idea to step back every once in a while to remember why we're trying to learn this stuff, right? So what we do as engineers is we creatively combine different components to make something really cool, right? To try to make something that benefits society in some way, right? So before I made the analogy that each one of our processes is like a Lego block, right? That fixing the state is like trying to find the pip on the Lego, right? And then each process is a Lego block. And then what we're going to do once we understand these open and closed system processes is we're going to put these blocks together to make something really cool, right? Now, unfortunately, it's not yet the Millennium Falcon, right? But it is stuff like a nuclear or a coal-fired power plant, right? So how do we put together components like pumps, boilers, turbines, and condensers to make something like a nuclear or a coal-fired power plant, right? So those are ones where the working fluid is water. But a natural gas power plant, right? The reason that the carbon emissions for the U.S. Have been going down over the medium to long term is because we're moving away from coal and moving towards natural gas, right? So when we think about trying to make these cool components, at least from the mechanical engineering perspective, when we're talking mostly about power systems like we do in this class, the blocks that we use to put together to make cool stuff are things like turbines, right? Remember, turbine, we have some high temperature, high pressure fluid that comes in that gets pushed over these fan blades, and that causes those fan blades to move, which makes this shaft spin, right? And then if we make friends with an electrical engineer, right, they can turn that spinning shaft into electrical power, which turns the lights on, right? We have pumps. Pumps are a little bit different because here we're putting in electrical energy that, again, with friends with an electrical engineer, right, that electrical energy is making a shaft spin. That spinning shaft pushes these impellers, right, which are like fan blades in our system, which move the fluid, right? We have throttling valves. Throttling valves are not super exciting. You probably have one. If you pull out the back of your fridge, you might see a throttling valve, or if your fridge is old enough, maybe it has a very thin copper tube that's coiled around in the back. Throttling valves, we'll see, are kind of boring. They're really just there to drop the pressure of the fluid without losing energy in the system. We have heat exchangers. Heat exchangers are really important components. You can think about something like the radiator in your car. I don't know if you've ever seen a radiator that's behind sort of the grill on your car, but basically it's got some tubes that are carrying radiator fluid, and then it's got some fins, right, to increase the surface area. So you're trying to cool off that radiator fluid as it moves through the radiator. And the way you do that is as your car moves, air moves over those fins. And even though you're not transferring mass, you're not pushing that radiator fluid out into the environment. It's all supposed to stay connected, right? But you're moving heat from the radiator fluid into the air as it moves over the fins. Right? And then we have nozzles and diffusers. They're interested in changing kinetic energy. And you may or may not have seen these, but the way I like to think about this is with a garden hose. So maybe you've done this with a garden hose, right? It's in there, it doesn't have any attachment on it, but you use your thumb and you cover part of the opening. And what happens when you do that is you shrink the area where the fluid is coming out, and because of that, the fluid comes out faster, right? So you're adding kinetic energy to the flow. A diffuser is kind of the opposite of that, where the area expands, and provided you're subsonic, then what happens is you're reducing the kinetic energy that's involved, or the velocity of the fluid, because it's taking up more area. So these are kind of the principal components that we might do an open first law analysis on, right? And in order to do these kind of analyses, we talked about in the thermofluid sciences, you unfortunately get cases where your equations have too many unknowns. So what we do as engineers often is we use our understanding of the systems that we're analyzing to try to determine which terms in our equation are the most important terms. But to do that, you sort of need a little bit of intuition, which we'll develop through the course. But I want to walk you through each one of these components and talk about assumptions that we might make to make that big, long version of the first law a little bit smaller, right? So, we talked about the reason that we're doing this is eventually we're going to look at lots of different systems like nuclear power plants, coal power plants, gas power plants, jet engines, automobile engines, and air conditioners, right? So we're going to be able to use the methods that we're still filling up our toolbox, right? So now we hopefully have a good idea of how to deal with closed system energy balance, and then open system energy balance, and then we're going to chain these processes together to try to model, to understand how all of these different processes, how all these different thermodynamic cycles or heat engines work, right? Now, when we think about at least the simplest version of a nuclear power plant, it's really just 4 open systems. A boiler, right? Something to boil the water. A turbine, which is going to extract work from the steam. A condenser, which is going to cool that steam back to liquid. And then a pump, which is going to drive the pressure back up. Right? So what we're going to do eventually when we do a first law analysis on something like this, a coal power plant, is we're going to do a first law analysis on all these components, and then we're just going to add the results together. Right? So we'll need to do conservation of mass and conservation of energy on all of these systems. So let's say we were dealing with something like a jet engine that has a diffuser on the front and a nozzle on the back. Right? So all of these components do some kind of a transaction. So the transaction that's happening in the nozzle and diffuser is you're trading kinetic energy for enthalpy. So either the enthalpy is going up and the kinetic energy is going down, that's what happens in a diffuser, or the enthalpy is going down and the kinetic energy is going up in a nozzle. So that's the main energy transaction that nozzles and diffusers do. So we're going to start with the first law, right? And it's an open first law. And in this class, all the problems are going to be steady state. So even if you got to an open first law problem on the second exam and you're like, man, I have no idea what to do, you can write down the first law and you can tell me that the system is at steady state. And because the system is at steady state, that differential term goes away, right? We're going to say for these nozzles and diffusers, when you looked at the pictures, that they usually only have, well, they're only supposed to have one inlet and one outlet. So my summation signs go away because I only have one inlet and one outlet. I wouldn't advise you to put your hand on like the nozzle at the back of a turbojet engine when it's operating, right? But it's probably hotter than the environment, right? Than the ambient temperature. There is probably some heat loss that's coming off that nozzle. But we're going to say that that heat transfer term is pretty small compared to the changes in enthalpy and the changes in kinetic energy. Because remember, that's the main transaction that's happening in these components. I also look at my nozzle and I see that it doesn't have any fan blades on the inside of it. It's all that's happening is the area is either going down or going up. I'm also going to say that the change in elevation of any bit of fluid inside my system is pretty close to zero. So that potential energy term, I'm also going to say, goes away. In that case, I'd get 0 is equal to the mass flow rate in times h in minus, or h in plus v in squared over 2, minus the mass flow rate times h out times v squared over 2. But if I did a conservation of mass analysis here, because we're steady state with one inlet and one outlet, the mass flow rate in must be equal to the mass flow rate out. So there's really only one mass flow rate in the problem. And what this tells us for nozzles and diffusers is that the change in the specific enthalpy is equal to the change in the kinetic energy per unit mass. So if the enthalpy goes up, well, the kinetic energy must go down. And if the kinetic energy goes up, like I'm covering more of the nozzle or covering more of the area of my garden hose, then what happens is that the enthalpy must be going down. I'm getting that extra energy from somewhere, right? And that's what the first law tells me. So if you have a nozzle or a diffuser, this is the analysis that you would usually do. These are common assumptions, but if you have an exam problem and I tell you that there's some heat loss, then you should include the heat loss in the problem, right? So you don't always make these assumptions. Turbines, right? So again, what happens is we're trying to extract enthalpy from a fluid and generate mechanical work in the form of this rotating shaft. So again, we start with the same base level equation and we make some assumptions. The first assumption always in this class will be that it's at steady state. For the turbine, although the example we're going to do today, the assumptions will be a little bit different, but oftentimes with turbines, we have one inlet and one outlet. If that's the case, my summation signs go away and I only have one inlet, one outlet. That's always nice because it means there's only one mass flow rate in the problem. I'm also going to say that the heat transfer term is much smaller than the power term, right? Or I could consider or pretend that the turbine is not losing any heat. Again, if you go to a nuclear power plant, don't like rush up and put your hand on the turbine, right? It's probably hotter than the ambient air around it. It's probably losing heat, but it's probably losing a lot less heat than the power that it's generating. We're going to say that the changes in kinetic energy and potential energy are approximately 0. That's something that we'll test out in the example today. And if we can do that, we see that the power generated by the turbine, W dot, is equal to the mass flow rate times H in minus H out. Excuse me. All right, so again, we started with the big equation, but because we can make a bunch of assumptions, we get a much simpler version of the equation. Next, we have compressors and pumps. They're essentially the same thing, right? But a pump operates on a liquid and a compressor operates on a gas. But they're both doing the same thing. They're putting in work, right? Often because you're plugging this thing into a wall, right? And they're increasing the enthalpy of the fluid by increasing the pressure. So we look at the pump. When we start with the same first law, we're going to say that it's steady state. We're going to say that it's one inlet and one outlet, at least usually. We're going to say that it's adiabatic, right? Or that the heat transfer is negligible compared to the power. We're going to neglect kinetic and potential energy changes, and we end up getting the same expression that we got for turbines. That W dot is equal to M dot times H in minus H out. Right? Now, here's the thing about turbines and pumps. We get the same equation. Because they're both doing the same energy transaction. They're both trading off enthalpy for power, but they're like on opposite sides of the trade. Right? So not long ago, I moved some money from Canada to the United States. right? So I sold some Canadian money and bought some American money. But there had to be someone else on the other side of that trade that was buying Canadian money and selling American money, right? Otherwise, we wouldn't have been able to do that trade. So turbines and pumps are just opposite sides of the same coin, right? I remember this equation because I'm trying to find work, right? And maybe it's because my girls are still pretty young, right? But we watch a lot of Disney, right? And I know that the hardest working people in all of Disney are the Seven Dwarfs. And the song that they sing goes hi ho, right? So if I'm trying to find work or power, it's nice to know what the answer's probably going to at least kind of look like at the end. And it's going to be the mass flow rate times the enthalpy at the inlet minus the enthalpy at the outlet, right? And it's going to follow this hip to win sign convention. So turbines, which are producing power, work is going out. Work out is positive. Pumps, work is going in, and work in is negative. So it's the same equation, but I expect turbine power to be positive and pump power to be negative. So heat exchangers might be the most complicated of all the components that we're going to look at. And it's because there's different kinds of heat exchangers, and depending on how you look at the different control volumes, you might make different assumptions. Right? There's sort of two kinds of heat exchangers. One of them, I always think about this direct contact heat exchanger as like, my grandfather had a sink, and when he was shaving, there was one hot tap and one cold tap, and he would take the hot water and the cold water and mix them together in the basin, and then he would shave using the water in the basin. And that's kind of like what the direct contact mixer does, where there's hot fluid coming in one inlet, cold fluid coming in some other inlet. They mix together, and then you get some warmer fluid that's colder than the hot fluid, but warmer than the cold inlet, right? And it goes out there, right? In order for this to happen, you need the same fluid, right? And it's got to be at the same pressure. Right? So oftentimes we don't necessarily have that. So let's say you're trying to cool off engine oil with water. Now you don't want the engine oil to mix with the water because you get something that looks like vinaigrette, right? That the oil and the water, they won't mix, right? So what you do here is you make something like a shell and tube heat exchanger. So maybe you have engine oil that runs through this tube and water in the shell, right? This water jacket that goes over it. I pump cold water through the shell, hot engine oil through the tube. And what happens is that oil is going to get cooler and the water is going to get hotter. Right? Just like we talked about, the radiator is also kind of like this, where your flow doesn't mix together directly. You have your radiator fluid, which is getting cooler because the air that's flowing over those fins is getting hotter. So there's heat being transferred from the radiator fluid to the air. So at least one way of looking at a heat exchanger, if we draw our control volume around the whole heat exchanger, we'll say that it's at steady state and that it's passive. There's no fan blades, so we're not going to talk about work that comes from, these moving fan blades. The weird thing about heat exchangers, when you look at the whole heat exchanger, is that we'll often say that they're adiabatic. And that's weird because a heat exchanger's job is to transfer heat. What this means is not that there's no heat transfer necessarily. It's that there's no heat transfer that passes over our control volume boundary. So if we draw our control volume big enough, all the heat that left that engine oil is going into the water. But if we look at the control volume a little bit differently, then this Q dot term might stick around. So we'll definitely do some examples of heat exchangers, and I'll show you the different ways you can work on them. Right? We're still going to neglect kinetic and potential energy. This is good, right? Because in most of the components we've looked at, the kinetic and potential energy terms drop out, and those are the ones where the units are the most difficult. So here, what I'm going to get, if I looked at the whole heat exchanger, is that the sum of the mass flow rates in times the inlet enthalpies minus the sum of the mass flow rates out times the outlet enthalpies are equal to 0. That the only energy terms we're interested in are the ones associated with the enthalpies going in and out. And what's happening is one stream of fluid will be getting cooler, whereas another stream of fluid will be getting hotter. I think this is the last of these ones, and it's definitely the most boring one, and it's a throttling device. The job of the throttling device is to try to reduce the pressure of your fluid without losing any energy stored in that fluid. Throttling devices are great to do the analysis on, but kind of boring, right? So they're steady state. They're one inlet, one outlet. They're passive. They're adiabatic. No kinetic energy change, no potential energy change. And what this means, because there's one inlet and one outlet and the mass flow rates are the same, it means that the inlet enthalpy is equal to the outlet enthalpy, even though the pressures have changed. So that's what happens in these throttling valves or throttling devices. The thing about these ones is that it's still important. Sometimes you see them as check valves in systems. They're just there to equalize the pressure. So let's say before you're going into one of those direct mixing heat exchangers, you want to make sure that you don't get backflow, that you don't, that you have one high pressure flow and one low pressure flow, and then you get flow going out what you think is one of the inlets. So you use these things to try to equalize the pressures inside devices. Oh, this shouldn't be here again, right? But this is just the idea that turbines and pumps have the same equation, right? So we're going to do this example on the same turbine we just did a conservation of mass problem for, right? So here, we already did conservation of mass here. So we have values for these different velocities, right? But now we're going to try to find the power generated by this turbine. Okay. So we will go, oh, I gotta open it up. So here's this same problem, but I wrote down the information that we found in the last problem, right? So in the last problem, we found these two velocities, okay? But now we have this same turbine, one inlet and two outlets, and we're trying to find the power generated from this turbine, right? It tells us it's a steam turbine, so it's water working through. And now we want to talk about the magnitude of the terms because I know these velocities. So I'm trying to say, is the velocity term important? Right, so the schematic is shown here. Right, this is, we have governing equations, conservation of mass. We used this already. That's how we found, that's how we found these velocity terms. But now we're going to do conservation of energy. Now, because this is a metric problem, when I wrote down conservation of energy in the kinetic and potential energy terms, I didn't have to divide by GC. Right? So here, I'm going to, even though this takes me a couple extra seconds to do, I'm going to write down every time I do one of these open first law problems, I'm going to write down the whole version of the first law. So dE by dt is equal to Q dot minus W dot plus the sum of M dot in H in minus V in squared over 2 plus GZ in minus the sum of M dot out H out plus V out squared over 2 plus GZ out. Now, I don't want to deal with all those terms, right? So I'm going to use some of my physical understanding of turbines to start crossing stuff out, right? So the first thing is we're interested in how much power this produces, presumably at steady state, right? It didn't say that here, but I'm going to assume that we are at steady state. I don't have enough information to calculate the heat transfer rate. If they told me that there was some heat loss from this turbine, then I would include that. But since they don't, I'm going to assume that this is adiabatic. There's only one inlet, right? But there's two outlets, so those matter. But I'm going to neglect kinetic energy changes. They're going to be approximately equal to potential energy changes, which is approximately equal to 0. So what's going to happen is this equation is going to become 0 is equal to negative W dot of the turbine plus M dot 1 times H1 minus M dot 2 H2 minus M dot 3 H3. Or that this thing that I'm looking for, the power from the turbine, is equal to, although we'll do it the fast way first, and then I'll show you what would happen if we didn't neglect kinetic energy. Because we have enough information here to include the velocities. So I'll show you what the base level of the equation looks like if we neglect kinetic energy, right? So this is going to be M dot 1 H1 minus M dot 2 H2 minus M dot 3 H3. This neglects changes in kinetic energy. But if I didn't neglect kinetic energy changes, then I would say that the power of the turbine is equal to M dot 1 times H1 plus V1 squared over 2 minus M dot 2 H2 plus V2 squared over 2 minus M dot 3 H3 plus V3 squared over 2. Right? And actually, if I look at those units, right, I know that H, if I look it up on the text in the textbook tables, this is going to be in kilojoules per kilogram. Right? But now this kinetic energy term stuck around. My spidey sense started tingling, right? And here I get velocity squared, which is meters squared per second squared, right? Which is the same thing as meters per second squared times meters. But Newton's second law tells me that force is equal to mass times acceleration, and that's an acceleration, right? So acceleration is equal to force over mass. So I can recast this as newtons per kilogram times meters, which is equal to joules per kilogram, right? But this one here was in kilojoules per kilogram. So I have to take these terms and say I've got 1 kilojoule per 1,000 joules. Then the joules cancel, and then I get kilojoules per kilogram. So I'm going to have to divide both of these terms by 1,000. In the equation, I don't include dividing by 2,000 every time, right? I just keep it as divided by 2, because if I was measuring the velocity of, say, an airplane or an automobile, I might talk about that velocity in terms of kilometers per hour or even, kilometers per second, although the number would be really small. And that's going to give me a different conversion factor. So I leave it as v squared over 2, knowing that I have to come back, right? From the previous problem, if I remember correctly, we know the mass flow rate at 1 was equal to 11.1 kilograms per second. The mass flow rate at 2 was 20% of that, or about 2.2 kilograms per second. And the mass flow rate at 3 was 80% of that, which was about 8.9 kilograms per second. So we know all of these mass flow rates. We know at least 2 of these velocities, right? One is like 10 and one is 17. I don't know what this one is. But let's put it in here. Let's just guess a number, right? Let's say it's on the same order of these, right? So I could say 17 or I could say 10. I could take an average. But let's just say let's say it's the biggest one here, right? Let's say it's 17, right? And we'll see if it matters. Not 7, but 17. Right? So again, we're at this place in thermodynamics where it doesn't look great because I've got one equation and 4 unknowns up here, right? And also one equation and 4 unknowns down here. But a bunch of this stuff is if I could fix the state, and I've actually already fixed these states, right? Then I would have 3 of these 4 unknowns, and I'd have one equation with 1 unknown in either different scenario. Right? So if you remember, state 1 was at 1 megapascal or 10 bar or 1,000 kPa. I think they also told us that the temperature was 500 degrees Celsius. I'm trying to find H1. So now I'm going to go down to my tables. Same tables. Remember before I said, oh, here's 1 megapascal. Right? Here's 500 degrees. It's 2 below the bold one. I took this value last time for the specific volume. But now, instead of doing specific internal energy like I would have done in a closed system problem, I'm interested in the specific enthalpy, which is 3478.5. And then over here, state 2 was 0.8 megapascals at 400 degrees. And I want the H value, not the U value. That's going to be 3267.1. Then the other thing I can do, remember they told me that the temperature at state 3 was 90 degrees and the quality at state 3 was 0.9. So here I want HF. Well, I'll take all 3 of these. HF, HFG, and HG. So they're going to be 376.92, 2283.2, and 2660.1. Okay, so let's get that all back up here. H1, this one was super heated vapor. H1 was 3,478.5 kilojoules per kilogram. State 2, which was also a superheated vapor, 0.8 megapascals, and a temperature of 400 degrees Celsius. H2 was equal to 3267.1 kilojoules per kilogram. The nice thing, we didn't have to interpolate with either of those 2 numbers, right? So now I look up here. Oh, I know H1 and I know H2. That's pretty good. Still need to find H3. Right, again, I asked, what's the fluid? Oh, the fluid was water, but the phase here, because they told me the quality, this means 2-phase, which means I can use my quality equation that H3 of X3 is equal to HF plus X3, this is HF at 90 degrees Celsius, times hg minus hf, or I could write this as hf plus x3 times hfg. Right? So this is equal to hfg. So it's one less thing I can screw up in my calculator because the textbook tables already did the subtraction for me. In the ones in the textbook, they have this for specific enthalpy, but not for specific internal energy. Right? So I'm going to use this because one last thing to put in my calculator. HF was 376.9 kilojoules per kilogram, plus 0.9, which has no units, that's my quality, times 2283.2 kilojoules per kilogram. I put that into my calculator. And assuming I didn't screw anything up, I get an answer of 2,431.8 kilojoules per kilogram. Right? And that makes sense. It's in between. Oh, so my so here HF was equal to 376.9 and HG was equal to 2660.1. These are both in kilojoules per kilogram. So I have this number, which is in between these, but closer to 2660, which makes sense because it's 90% vapor, right? So now I have H1, H2, and H3. All right, so I'm going to go back to the slides now to show you what happens numerically. All right, so here, this was the same thing. Let's come down to... All right, so here I fixed the states. Right, so here I just, because we were at 10 bar and 500 degrees, so we pick off this number. Right, we put it in our state table. This was at 0.8 bar and 400 degrees. So again, we just pick off the value. We didn't have to do any interpolation, which is nice. And then for the quality equation, we look at 90 degrees. We go all the way over here to H, to the H values, not the specific internal energy values. And I get an answer for that. All right, so I have two different models here. One where we didn't neglect kinetic energy, and one where we did. Right? But for this, we had to estimate what the first velocity was, right? So let's look at all three of these individual terms and say, is the kinetic energy term important, right? Actually here, I think when we were going over the example, I said, well, let's pick 17.1, but here it looks like I picked 10, right? Let's see if it matters. Let's see if my estimate matters what the velocity is, right? Because that's kind of the question that we're asking. One of the questions we're asking is, you know, what's the power? But the other one is, does the kinetic energy matter? Right? So here, I've got two different terms here. So I can take 11.1 times this, 3475, and I get this, right? And I can and then I can take 11.1 multiplied by this, right? And it's 635, but I didn't fix the units yet, right? This is still in joules per second, and this is in kilojoules per second, right? So actually this 635 isn't even 635. I got to divide by 1,000, right? So this is like, 38,500, and this is 0.6. So you can see here that the kinetic energy term, even though we're squaring that velocity, it doesn't really matter, right? It doesn't matter if I picked 10 or if I picked 17. As long as it's not like 100 meters per second, we're probably okay, right? And even then, it might not get all that important, right? So here, the kinetic energy portion of this term was, a fraction of a very small fraction of a percent of the total energy, right? So here in this first term, it would have been fine to neglect the kinetic energy at this first port. Right? But what about the second port, right? So in the second port, the maybe the velocity term is important, right? Because it's 17.1, right? And we square it, right? So again, I got to account for the fact that that's joules per second, so I divide by 1,000. Here it's more important than it was, 4 times more important than it was, but it's still really small, right? You got to have, you basically, I would say almost never in an engineering application are you going to care about being that precise. That is a very, very small number. So neglecting that kinetic energy wouldn't have mattered, right? And then here, right, again, not surprisingly, right, spoiler alert, it also doesn't matter here, right? So if I include kinetic energy, I get that this turbine produces 9,750 kilojoules per second, right? Or if I divide by 1,000, right, then that becomes 9.75 megawatts. Now, what happens if I neglected kinetic energy right off the bat? I think you know what happens, right? Because the kinetic energy wasn't important. Now I just took the mass flow rates at each state multiplied by the specific enthalpies, right? And I get the same answer, right? Unsurprisingly, when in each term the kinetic energy wasn't important, that in the sum of each term, kinetic energy is not important. So usually, for turbines and pumps, for heat exchangers, we usually neglect kinetic energy, and potential energy ends up being kind of the same thing, where it's not that important. The one exception, though, for kinetic energy is when we have a nozzle or a diffuser, because the energy transaction that it's doing is it's trading off enthalpy for kinetic energy, right? So kinetic energy is really important in nozzles and diffusers, right? So for us, when we end up talking about heat engines, that means kinetic energy is really important in turbojet engines, so the kind of engines you'd see on a jet plane. But other than that, kinetic and potential energy probably aren't going to be all that important. So that was the last slide of the lecture part. Are there any questions about how we did this open first law problem? All right, we can take 5 minutes. We'll come back at 8:34, and then we'll just have kind of an open session. And if you have questions about the upcoming exam, then I'm happy to try to answer them now. Or at least I'll be happy to answer them in 5 minutes. All right, I'll see you in a sec.